just using when I was visiting them, and then I got some materials back, and then using those materials for some interesting, phenomenon for exploration purpose. Just trying to put it in, to learn a little bit more about the phase separation. How do you control this using liquid crystal to control the polymer formation, and then using the light to control the phase separation kinetics. So those were kind of information we're going to learn today. So I guess we continue on to the yesterday's part of the lecture. Because we are working a lot of these composites using polymer network and liquid crystals. So certainly there are different type of liquid crystals. So we need to learn a little bit about the effect of liquid crystal phase on this polarization formation of polymer network in liquid crystal, and then you think about it, what can you do application with that. So in general, what you learned yesterday is there are two types of materials. One is soft, both of them are soft materials. One is polymer. It means a macromolecule. It could form linearly if you hold your hands all together, cross. But if you hold your hands randomly, and you may cross over the other people's hands. So that's called three-dimensional networking. So in that way that you may form some kind of structures that disrupting the original orientation. So, in general, is you need to throw in some of the material that can form this three-dimensional network, and the concentration. So the spectrum is like this. Okay, this is the high-end polymer. This is high-end of the liquid crystals, right? And then so it depends on what the composition is. More like emulsion. Water in oil, oil in water. Which one is the host and which one is the guest? So in general, here is sometimes more polymer has some advantage, but on the other hand, you also trade off for some important parameters, for example, performance of device, light scattering issues that you have to deal with. So you need to have some kind of alignment. You need to use liquid crystals as kind of host. That gives you more advantage. You can orient them in the vertical direction, in the parallel direction, in the twisted structural direction, in a one-dimensional this periodical pattern. So you have this liquid crystal reach, the other heterogeneous material reach. So in that case, that you can have this ordered structure. So you want that polarization means forming this networking structures takes place. With minimum distortion, minimum distortion of this original liquid crystal alignment. So that's important. Let's see. So you want the structure form that you can retain the original shape and size, and you may want to think about what's important here. Why I'm learning this here? Because of the textures used can be created for something. For example, maybe can be used that as for making something food like a pasta dumpling. Like in Chinese dumpling pastas. In Western countries. For your table. And we will see how we're gonna do that. So in general, you need a surface alignment. I think Ivan gave us some nice, overview yesterday. You need to have some kind of orientation. So you first of all, you need to have some kind of surface alignment layers to make a specific structure, and then you may be creating this orientation with a surface alignment, one substrate aligned in the direction parallel to the screen. And the other one with the orientation perpendicular to the screen, so you get twisted structures. And in this case, that the free energy of the system is not zero anymore, so it requires some kind of a minimization of stability issues. And if you put in another heterogeneous species, that's going to cause some kind of disruption of this your orientation, so of your host. But if you have some alignment like this, you have this alignment, for example, Robin direction in this direction, Robin direction in that direction. say parallel to each other with respect to the Robin direction. Okay, so they are now at 0 degree differences. And in that case, if you can create some small pre-tilt, for example, 2 degree to 10 degree, even sometimes people even thinking about 45 degree. So you get this pie shell-like structures. This is more like pie or spray, actually, of your directors of the liquid crystal. So in that case, that these systems require some stabilization. Otherwise, the system, the free energy is no longer 0. So it may create some kind of defects or structures. On the other hand, if you have some orientation, more like those VA type of this device, they also need to create in some kind of in the actual orientation direction. So the device, that TV you have, manufactured by the majority of the manufacturers, they have this slight soft buffing of the surface. Okay, so when you turn the field off, they can go back to the same direction without creating any defects for flow, and that's important. Okay, so you got the order in the very beginning. You put it in some heterogeneous species, and with that you can create all kind of defects. And defects is not the topic of the study of this subject here. So I will just skip that. So you have this species start to form, and then distortion is also unfavorable. So your system want to minimize the energy. So that's a kind of a general process. You coat the substrates with a layer of polymer. Polyimide is normally used for this orientation layer, and then you can assemble them just like what I described earlier. Okay, so in the case of you put in the other soft material, for example, soft material, sometimes you have this gel-like materials, and they have this functional group on each end, or you can have functional group even more than that, more than 2. To make a 3-dimensional network, you need to have each person needs to have 3 hands, at least. 2 hands cannot make this 3-dimensional network, because you can only hold the other person's hand. The other hand you can hold the other person's hand. So with that connection, you can only have it's 2-dimensional. So to make the network, you have to be randomly kind of connecting your hands with your neighbors. So that's the kind of advantage or strategy we have here. So with this type of material, they are the rod-like shape. They have a functional group at the end for this forming this network, and then you need a small amount of this photoinitiator, and certainly you need a liquid crystal host. This host can be pneumatic, somatic, charismatic, banana, cholesteric, blue phase, anything you were thinking about that can form in, or maybe lytropic pneumatic like disodium glycolate like the DSCG forming this lytropic pneumatic. Okay, so in general, when you put in this, as I said earlier, we put in less than 10%, maybe few percent into the host, and you form in a mixtures, a uniform mixture like that. And then once you use some methods to induce the phase separation, there are multiple ways to induce phase separation. Using the light, using the energy, energy, and then they start when they nucleate. You see, they nucleate at some defects area. They start if your surface is not clean, has some dust particle, and they start to form those polymer networks from. And then under microscope, we can see those defects, a dark spot, right? Because it destroyed the alignment, and then you got the defects. So you see the defects under the cross polarizers microscope. And you see dark spots, and then they start to grow, getting bigger and bigger, and finally forming a Chien slide. When critical mass reach to some certain degree, and then these networks start to connect to each other. So I think the size of that, the size of this nodular beads or whatever fibrils that you call this, is a kind of a function of this temperature. Certainly is the viscosity that control the diffusion limit. So this is also the reaction rate, the phase separation rate that we discussed yesterday. And then it's also proportional to the concentration. So the size of this is inversely proportional to the rate of phase separation. So if you are shining the light to use a huge light, turn on too much of this, turn on too many lamps, they're gonna cause this phase separation goes very quick, and that's the problem. If the phase separation goes very quick, the nodules that you see, the defects of those is getting smaller, smaller and denser, and creating more defects. So you have to control that. Certainly, if the media, the viscosity of the host is also determine the diffusion rate. So, for example, just quick quiz, okay? Which one has higher viscosity? Pneumatic, somatic A, chirosomatic C, cholesteric. Which one has higher viscosity? Does everybody know? You buy some liquid crystal mixtures from Merck, right? So you get 3 bottles, okay? Ferroelectric liquid crystals. You get the pneumatic, you got the cholesteric. So which one will have the highest viscosity? Does anybody know?
I would say the cholesteric.
Oh, you will the cholesteric. Do you all agree with him? No? Okay, somebody said no. Anyone else?
Ferroelectric.
Ferroelectric, yeah, very good. Why is ferroelectric that has the highest viscosity? You see that people are forming in layer structures, right? To move, disrupting those layers, it takes more energy. Okay, the cholesteric is a very pneumatic-like, as said, that they just twisting layers. So I think that's a very good question. Good answer that is cholesteric. So you form this. You see that this is the reason that we want to learn this a little bit. Because of using a small amount of polymer to modify these ferroelectric liquid crystals. Originally, this Ivan yesterday showing that the molecules have been responding to applied fields. It rotates the dipoles in the direction in the motion of cone angles, right? So if you have a small amount of polymer, you can suppress in that cone rotations back and forth like this, back and forth like that. Instead of rotating through a cone, it stays in the plane, more like electroclinic effect, right? At the same time, learned the electroclinic effect before. Between the chirosomatic A and chirosomatic C, there's a very small degree of angles. The directors only rotate in the plane. So in that case, that you get a great scale of these devices of FLC. That's why they are 45-degree type of tilting FLC device molecules. It's very important that they give you this kind of great scale. But without that, by using small amount of polymer, 2 to 3%, and you suppressing that cone angles, right? So the polymer will form in between the layers, more like this layer, that layer, So when the molecule in responding to apply the field, they try to tilt in out of the plane, and then they get compressed by this polymer network. Okay, so that gives you the that gives you the somatic chirosomatic A like a switching, So something like that, you see, is very important, right? Fundamental temperatures controls everything. Thermodynamics, these factors control the, diffusion rate, reaction rate, and something like that. Okay. So without further consideration of this, the rate of reaction, like your monomer concentration, your the quantum yields of the light absorption, and then the light intensity, and if you use light to shine this material to make the phase separation, and then the cell gap, the length path. Okay, so you can see that these pictures, SCM pictures, are very similar to that, right? So it looks like natural light, small beads connected together. It can also form fibers, if the control of this phase separation is not carefully happen. So I guess it involves a little bit. It involves a little bit about the free energy of the system. It includes the elastic energy of the system, the surface free energy, and also the mixtures. The mixtures means containing this two different components. For example, that two different components depends on concentration of monomer, concentration of liquid crystals. So this Fourier-Hawkins these equations should be the power should be added into this total free energy system because of the surface energy. If you have a surface alignment, depends on the structural deformation, and that one is kind of a minimum. But I think the control factors is here. The control factor is the free energy of the system, elastic free energy, and also the phase separation. The mixtures they forming this. Before phase separation, they have also before you use the external energy to induce this phase separation, they have this premature phase separation. Okay, so that's kind of factors you need to consider. The others, the free energy is anchoring, is polar anchoring energy, and also this azimuthal anchoring energy. Not determined by your manufacturing process. Did you rub it strong enough? Creating the group structures periodicity small enough to have this combine this to make sure that the deviation of that orientation of your directors. Okay, the director in the plane did not interfere, because of the cell gap effect. And then the tilting angles, the deviation of that, everybody from the first layer up to lay following the pre-tilts of the surface. Okay, so I guess something like that is what we were looking for. Okay, the first case is the material that you see here. Here's the carton here. Okay, the carton show you that it's more like a molecule susceptible to the light. If you can chop them off, forming free radical. This free radical can find those double bonds to form this network. And then sometimes you can use the methods to control the anisotropy phase separation. Have them only localized on one. The carton it's a little bit slower. Maybe the weather slow it down. It's cooler to go faster. So I guess they were kind of all localized on one surface, and then give you some of this orientation. And those the polymer network only localized at one surface. And here's one example. If the cell is about 10 micron thick, and then they only form about less than a micron, half a micron on one surface. Okay, certainly the other side has the same kind of concentration in the bulk. It's a very minimum. Sometimes may have a few fibrils, but when you tell them apart, when you open up the cells, you couldn't see too much. You break up these fibrils. The other is if you have homeotropic alignment, and you can see that those polymer fibers forming perpendicular to the surface. Okay. On the other hand, that you also have on the other substrate, you also have a similar effect. And then sometimes if you can control this phase separation and much slower, so you can form in the area that where you want them to go. Okay. So instead of all localize that, the thresholds of this light intensity to form this phase separation is within the cell gap. This is the cell gap. Okay, that's the cell gap here, the D. And then the light intensity across the cells is all above the minimum, the threshold. Okay, so it induces everything. But let's go back to the previous slide. You see the previous slides, you see that this is the thresholds of light intensity, right? But this threshold of light intensity only within the certain distance of the front substrate, right? Only within this maybe 1/10, 1/5 of this light intensity, and then oh, now it works. Okay, well, when you don't want that noise happen, it works. Okay, so that's the case. So you see that the majority of the cells, the light intensity is fall underneath this the threshold. Okay, to require that the chemical reaction happen. So that's kind of a process. Okay. So that's the carton here, and then so we skip this. So in general, if you have alignments of the cells, and then you control the UV light condition, in that case these cells, you see that it forms kind of a fibril-like from the top of the substrate, and that's a concentration of the this polymer roughly around 6%. You increase that, higher concentration, and you see that the more dense of the network. And then, in fact, this is only surface alignment. And you can see that periodically they form a very nice fibrils connecting to top and bottom substrates. So by controlling this, changing this kinetics of phase separation, you can see that the distance of those fibrils can, if you increase the polymer concentration, it can start from several almost millimeters, half a millimeters to about less than 150, around 50 nanometers, microns. I'm sorry, 50 microns. By distance. And then if you change that initiator concentration, you increase that the rate of phase separation. And it goes much further from almost 2 times when you increase the concentration from it's 1 to 4%. I guess the micron is just like the weather here. It has temper. It changed the condition quite frequently. So let's give a try the other one. Okay, hopefully this one works. So the other one is we using this the light intensity. So you can see that they also have a trend that decrease in the distance of those fibrils and also polymer walls between the boundary when you increase the light intensity. And then if you change the temperature, you see that the temperature from 25 to about 40 degrees. And it is the distance rise, and why is that? Because of when this temperature getting warmer, people's activities start to feel like uncomfortable. When the room temperatures rise, you don't feel like you want to sit here longer, right? So you want to run around. So what does that happen? You're trying to find your partner holding the hands. It's more difficult, right? And that's why they separate much farther. You don't want to sit too close because of you raise the body temperature, right? And then you feel like you want to cool down, so you want to get away from your partner. So that's kind of simple interpretation. Okay, so here is the work that we work with is Dick Bohr of this Dutch group. So the materials that they publish in different places like macromolecules and also liquid crystal. Here is kind of a functional group on one end, and then and the others is double bond. So this type of material, if you find the photoinitiator take off that hydrogen, it creates 2 free radicals. And in general, in principle, it will find a kind of a partner like that and forming a kind of a connection. And then you have supposed to chain transfer. So here is a complicated chemical structures, this polymerization mechanism. So we will kind of forget about the detail. Only see one picture here. Okay, here's the head and tail, right? So the connection is supposed to be head and tail, head and tail, head and tail. Unfortunately, when it forms that, there's a kind of a metastable state of the free radicals, electron. So you may find also the other double bond to connect it. So if you are able to control this kinetics by fix one of the molar concentration 5%, by changing of one of the components concentration, and then in different kind of hosts. Here is the pneumatic, somatic, and then cholesteric, right? So that's what I was suggesting that. So you can see first things in the pneumatic, it's kind of interesting. Well, if you have a surface alignment, it aligns in the alignment direction, and then it forms a very uniform size in terms of size. And this is more like microscope pictures, but here is the SEM picture. Well, in some alignment areas, it forms a very, very well organized shape. And these shapes look like either bow tie or your mustache.
And the other one in the non-alignment regions, it forms more radical. It has freedoms to go anywhere to minimize the energy, so you can see more like a flower-like shape. So if you lower that concentration, slow it down, and then you can also see this domain size is kind of very uniform. You see the domain size is very uniform, and it opens up that structures. So what does that tell you? That tells you something, right? The second one is in the ordered semantic phase. You can see that they form these ordered structures, and then the ordered structure forming also very well organized these features. First one, since you can see that this is more like dumpling. I don't know if you have a chance to try this dumpling in this country, And then you see there's the ingredients written around, so you can put them into your hot pot and boil them. The other one, if you're from Europe, you probably prefer the pasta instead of a dumpling. So you can see that they can form a pasta or the dumpling with very nice, in terms of structure. If you slow down that nucleation process, and then you can see that they give different kind of shape. Okay, so everybody is interested in this ordered structure. So periodical patterns is very important. How do you generate that in terms of this type of materials? We can use cholesteric. I think Ivan also showed possibly forming these periodical patterns. And then you can generate that by changing the pitch size. So one of the lines, the space between two lines is equal to half a pitch. So you can tune that by whatever changing the helical pitch of the cholesteric. So you can see that they phase separate very well before phase separation. After phase separation, you remove the liquid crystal. You can see they well align the structures. And then those materials kind of after removing liquid crystals, you can see the features more like this, and those outside of alignment regions, they have their freedoms to do whatever they want. For example, like you're sitting far away from your teachers or your manager, then you can do whatever you want it when he's talking, or he's screaming, But if you sit too close to your manager or your teacher, you have to behave well, right? So that's called a director effect. So we call that director effect. It's closer to the directors, then you have to follow the rule. By slowing down the phase separation process, you can see that the features are quite different. Okay, so we don't need a summary. I just quick showing you before we take a break. Volodomir recently did some interesting work. We have this liquid crystal directed polymer nanostructures. So, just study some of the response time function of polarization and study this TV curve as a function of polarization condition, and then comparing this morphology as a function of this polymer network on this electro-optical. But the detail I will let you talk to is Ivan. Not Ivan, is Volodomir. So I think the conditions like this, you need network forming materials roughly around 3%, and you need to have a liquid crystal that has this negative dielectric anisotropy. So you need to have a surface alignment layer with homeotropic aligned material, and you shine a light phase separation. And so the interesting thing is to control the kinetics of phase separation. We just mentioned here. You can see that there's phase separation. So we use the bandpass filters to filter out most of the light. Anyway, the glass substrate also cut off a lot of light. It does not allow the transmission beyond 315 nanometer. So there's only a small region of light we can control. So the idea is we want to have an anisotropy phase separation. We want polymer networks only localized on one substrate. So that's the one kind of effect. And that's useful. Okay, in Philips, I think they introduced this single substrate in 2004, 2002, and I visited them in 2003. And they have a problem with separation with creating this dome for one of this surface like that. And then in fact the cartoon you can draw is quite flat. In a real device, it's kind of curved up more like a lens. Somebody this lenticular lens-like shape, so it's not uniform. So the contrast, once you apply the field, is in the center of the pixels, it turned off. It's not fully turned on, but on the edge, it's turned on. So what's happening? You get the lousy device only suitable for maybe toy or some kind of application instead of high-end application. So with that, I think we were able to control this. And here is one of the pictures here. You see that sometimes when you shine and they quick response, they form in big multiple smaller structures. And then in some cases that you can control them, and then they form much smaller domains, which is smaller than the wavelengths of light. That's why microscope couldn't pick it up. Microscope couldn't pick it up. I think the battery all went down. So we have about 10 minutes before we get in the break. Just counting that. So you see that it creates some defects. If you have too fast of phase separation, you create bigger domains. Dense network, and then creating longer fibrils. But how do you know? You look at the microscope pictures. Does that tell you all the story? No, right? One characterization method doesn't tell you the full story. So you have to study different kind of using different methods to explore it. So before you open up the cell, so you want to study this electro-optical properties. So you take it to the setup and make sure that this light transmission is a function of applied voltage. So for VA mode, the molecule starts with vertical alignment. You apply the fields. And then they start to rotate, and then with dipole align in the direction of the field. So you get an increase of this light transmission as a function of the voltage increase. And then there's a ratios because of the type of liquid crystal that you use. So we see that with different kind of feature. This one, the first one is the one has no, it's a control, right? So you always have a need to control. That has no polymer, and this one has some polymer. And this one, with polymer without filters, and then there's a handheld, different kind of light condition. So you see that different kind of structure forming. You see different kind of contrast between the dark state and bright state. So I think the response time in terms of that, it shows some of the compared to the original, and then some of them did not change too much in terms of the turn-off time. But in the turn-off time, I think some this network growing longer, bigger, it costs some energy to reorient the liquid crystal. So it takes much longer time. Before time, you can see that some of the network is kind of a nano structure, and it gives you much faster. So what controls the turn-off time? The molecules, homeotropic alignment. You turn it on like this. When you turn the field off, they have to go back, right? They have to prevent this back flows. And then what kind of energy that you have to control them rotate or reorient back to the original state? It's only surface anchoring, right? Because you have surface homeotropic alignment, and molecules more starting original condition like that, they get reoriented by your fields in responding to your applied field direction. You turn the field off, they can go either way, this way or that way, or the other way, right? But you have alignment that they and wrap it a little bit, so they will go back in a concerted motion. As in this way, if you have a network that can go back faster, so let's go take a look. Okay, we have 3 more minutes before taking the break. The polymerized filters, you can see that in some cases, both sides still see some elongated these fibrils. But here is the 1 micron scale, so you can see those tiny dots. Fibrils is about 100 nanometer or smaller, and on the surface they just stick out very little, right? Okay, so if you control that, you try to change the conditions. Still, you see some big glob because of the conglomerate of these fibrils, and then most of that they find they form very ordered dots here. Well, if you use the low intensity, they grow much fast, much slower. They get a chance to diffuse and nucleate. and you can see some of the fibers grow longer, and this is 5 micron scale, so they grow longer. And then they are very sharp. Did you see that? On the surface, some of them they grow very sharp. But in the case of without filters, we can try to localize on one surface, so the cell is kind of illuminated with the UV light for both sides at equal amount of time. So you can see this. You see the domain size is a tiny bit. Always enlarge that a little bit. This is 10 micron scale, so that's about 1 micron. You see that? So each domain is more like a candle. If we continuously enlarge that, that's about 1 micron. And you can see that's 1 micron, so roughly they are about 100 to 150 nanometers. So compare those, you can summarize the different type of shape, And so I guess I stop here for break and answer your questions.
Are there questions?
Well, you can take the pasta or dumpling home for lunch, so save your money for lunch.
Okay, if not, we'll resume in 10 minutes.
So, your attention. So, about the book, ticket for train, we have to pay some actual fee for booking it. It's 6 yuan. So we can give the fee to give the money to Jiang Li just outside this factory. And also, who want to buy the new ticket also can buy from Jiang Li. For additional.
Again, just like what we learned yesterday, right? So chirodopin is very important. It's induced the blue phase. The others, some of the liquid crystals also showing this blue phase by itself. So what is blue phase? The question is, what is blue phase? Here's the pure image of this just samples put it in between two these pieces of glass slides, and look at it under the polarized microscope, and you see in the refraction mode, not the transmission mode, in the refraction mode, and you can see that these break refractions of these materials. It shows 3 types of these blue phase structures that has been known since in the 70s. So this, so the reason is why are you interested in this? Why does people going back to revisit this? In the past, this is kind of materials that exist only somewhere around 1 degree between the cholesteric and the isotropic. And I think we also have an expert here, Professor Cole, doing this quite a bit in the 80s, maybe even in the 70s. I forgot. So there are some kind of double twisted helix, forming by this cholesteric, and then the students, Lulu, did this work in last fall semester, and then so the materials are basically forming the BP phase 1, BP phase 2, and BP phase 3. So the structures are symmetry group for those cubic symmetry, they are bicenter cubic, and then the BP2 is more like a simple cubic. So this BP3 is almost isotropic, close to the isotropic temperatures, and they are within the range of 1 to 1.5 degrees Celsius. So with that is, in the past, people very carefully control that and then study their physical property, and they are also, studies much earlier, in terms of their electro-optical effects. So there are 2 types of electro-optical effects you can expect from such kind of materials. So this kind of blue phase materials shows this field-induced Kerr effect. What does that mean? The Barrington's It's kind of function of applied field strength, and that's proportional to what's the kind of periodic structures, the elastic constants of the blue phase, and then the square of the field. So these are K curl constants. K curl constant kind of sometimes in the range of, in general, 10 to the minus 9 to 10 to the minus 10 volts square meter. And you can go back to more earlier work in this area. So as I said earlier, they appear in a very narrow range, the temperature range, and then they're useful for field-induced barringtons, and also they're useful for some kind of break reflection. And so the first part of this presentation will just focus on this field-induced effect. The field-induced effect actually is not very new, and there are quite a few papers. But recently, I think they possibly forming some kind of light modulators displays with a speed of 10 to the minus 4 seconds. That means about 100 microseconds range. And that's attributed to the local reorientation of molecules by electric fields effect. And this type of effect that you have to view through the cross polarizer. Okay, and the color, how would you generate the color in a display? Just quick questions. This summer school, so make sure that we have some bright students and we don't miss. Anybody have answer for that? How do you generate a display with a color? Color filters, right? You have a sequential arrangement of your color filter. The light transmitted through your device that are passing through a particular subpixels of your color filter, and then that gives you the color. So if you want to have a mix-up of color, you can maybe turn a 1/3 on, 2/3 on, or maybe have all of them on, you get a white, something like that. So in this blue phase device, you also need to this curve effect. You also need to have a color filter, okay? And so here is a kind of a simple structures. That's just to show you that the field-induced barringtons effect. Since they are isotropic materials, you don't need an alignment layer. That's kind of advantage. It's been known for years, so this is nothing new. Just showing you the cartoons of that. You putting them into the cells, and then in general, in the dark states, they are kind of very symmetry. In terms of the optics axis distribution inside of cells. And then actually this in-plane field size also known quite some time. It's not just recently known. And then when you apply the field across, you kind of between the electrodes, right? Between your interdigitated electrodes, you apply the field across a cell on the top substrate doesn't have electrode. So there's a Gaussian distribution. You can do some modeling to see the distribution of the electric fields across the two electrodes, and then with the space of this cell gap. So I think so with this kind of condition, you need to kind of optimize them to maximize this electric field, because we just mentioned here that the field-induced barringtons is a function square proportional to applied field, right? So it's very important that you maximize that, so you get the maximize of this induced barringtons. So between the dark state and the bright state, right? If you have across the fields, across polarizers, and then in the dark state at 0 voltage, and then you want to apply small fields, save your energy, but it can induce the maximum contrast, and that's important for this factor. So optimize this structural electrode properties is a kind of important factor. So advantage for this type of devices, including this alignment-free, it's a cubic structure, in-plane switching field, they have fast turn-on time, they have a high contrast, wide wind angle, but they also have some limits. What are the limits here? They require thick cell gaps to induce enough barringtons between the dark state and bright state. So the dark state and bright states need to be enhanced by use of thick cell. And normally they are chiral materials, right? This is the reason that we want to learn the viscosity of the material. Cholesteric is already very high, and you trying to twist the helix smaller and smaller, to form this double helix, and then what does that mean in the induced blue phase material? Okay, we're talking about the induced blue phase material, not the intrinsic blue phase material. So you need to add a lot of these chiral additives, or using some kind of chiral additive that has a high helical power. So that's the alternative. So this slow turn-off time is another issue, right? Or why is that another issue? Because of when you turn the field off, you have to go back to the isotropic state, right? So that relaxation process takes a long time. So this is the kind of material you normally use in pneumatic liquid crystal chiral dopant, and then in general, they roughly around the pitch are about 0.2 micron, and that's smaller than the wavelengths of the light. So normally in this neo UV or this deep UV, in the deep UV, in the near UV. So there's a local field directed orientation roughly around 10 to 100 microseconds. Depends on how you formulate these materials, or how do you using the different kind of structures that, for example, maybe increase these defect structures, stabilize that defect structure, and then blue phase transitions to the chiral pneumatic cholesteric roughly around second to a minute. Okay, so if you carefully formulate the material, sometimes when you apply high field, and it goes back to the transition to the cholesteric, and you get photoconic texture, and it takes a long time to recover. Okay, what you have to do is you have to heat it up and cool it down, heat it up and cool it down, slowly. So that's an issue here too. Normally people don't discuss that when they publish the paper. They're trying to hide the defects, behind it. But they show the perfect side. Okay, so you have to ask questions. That's why I'm saying you have to ask me questions when you see something you don't feel comfortable. So this field-induced variance, you see that if in the case of that, it's also cell gap is an issue, and then the response time is proportional to that rotation viscosity of the material, the pitch length, certainly that's and this elastic energy of this blue phase material. So here's just one example. You have a blue phase material going to almost isotropic, it cooling down slowly, and you can see that blue phase domain forming. And in some cases, you see some cholesteric form. So that's something. That's one example. So in the cells that used for this study, then as we say that we need to kind of optimize this effect of this cell gap, and also the pitch of the electrodes. Certainly, the width of the electrodes are also very important. But for lab study, it doesn't matter. For this industrial manufacturing, since they have this implant switching, trying to eliminate this disclination line, light leakaging to give you wide wind angle. The zigzag electrodes is more like instead of straight. Okay. In the TV that you buy at the store, if it's IPS mode or super IPS mode or AS IPS or whatever ultra IPS, they put the name on, they can sell you more money. That means they are trying to optimize their viewing angles by eliminating those flow effect and also the defects at the zero voltage or field on state. Because you see that on top of the electrodes is zero field, right? So that area it doesn't switch, So, but anyway, for left is study that this can be improved. So here to show you something here. For example, the cell gaps different cell gap effect for 5, 10, and 20 microns over here. You can see that 5, 10, 20, and then this the cell gap effect, and you can see that it shows some defect lines, and defect lines perfectly sits on top of this electrode. The electrode width is about 10 micron. Okay, so the 10 micron pitch, and then you can see that field-induced divergence is gradually increased, and to some extent, when you apply higher field, you see that the other phases may be showing up, defects problems showing, and the cell gaps are kind of getting bigger and bigger, and sometimes it can return it to this domain size that after switching it can grow. So this is more like field effects increasing, and you can induce divergence. Certainly higher fields you can induce higher divergence. So in this case, that because of the break reflection of this type of device, when you apply the implant field, it doesn't shift. Okay, it stays about the same. You can see roughly they shift around less than 30-40 nanometer, and in the visible, and it's also blue shift. Okay, so this device also blue shift as a function of applied field, and that's the break reflection wavelength, and that's the just images of a microscope showing you that in fact roughly around there's 40 volts in these samples. There's a 1055. The sample is a 10 micron cell gap, 5 micron electrode, and 5 micron space between the electrodes. So you can see that the cell gap effect over here, it gives a pretty nice of this contrast between the dark and bright states. Okay, so you like to compare those. So we see that here the first one is the cell gap effect, the 5, 10, and 20. So in those cases that the cell gaps sometimes when you have a thicker cell gaps and then you have applied high field, but you did not switch fully on, right? You have to use a higher voltage to apply. But you know what? The materials that you have may not be so clean. What does that mean? When you try to drive it, you also use about kilohertz, But this material has some ions, effects that causing some of this direct heating. So in some cases, if you apply the field high voltage, it may cause some kind of dielectric heating. So what does that happen to your roof face? If you hit the sample up, it varies, right? The lattice structures change, and maybe unwinding, change to the other phase, and then so that's why it may not be so stable. But at the small cell gap, we can see that the high voltage can switch that to a higher transmission state. So here is the 5-5. There's a 5-5 cell gaps. Electrode space and line, and this is the 10-10. So this 5-5 and 10-10, you see that the fields are kind of what you require to switch that to get about the same kind of contrast. It's roughly much lower in terms of the threshold. You see threshold here about 30 volts, and then the threshold here roughly around 50 volts. But turn on time also reduced. So I think optimizing this is important. So we have this electrode effect, and then I compare that. So for those electrodes, the 5-5 and 10-10, and you see these break reflections also roughly stays the same. They shift a little bit, blue shifting into the shorter wavelengths. So the question for you is why these materials are responding to applied field, shifting their break reflection spectra to the shorter wavelengths? Means the blue shift, right? What does blue shift means? You have a square lattice, right? You have lots of squares, cubes inside of the cells, and the cells is more or less comparable to the wavelengths of light. And then you apply the field, they shrink, they get compressed, right? And they change the size structures, And then so that's the reason that you see a slightly shift. And the response time wise, I think in general, if you do some calculation by the materials, and then the pitch, so roughly the viscosity of the materials. If you estimate that, and then you can estimate that the elastic constants, and so the response time roughly around 800 milliseconds for this type of materials. So eventually you can do some estimation from here. But once you measure that, you can determine this by changing the cell gap from 5 micron, 10 micron to 10 micron. The electrode space from 10-10 to 10-10 stays the same to about 5-5. So you can see, the best. Let me see. Oh, I see. I missed that. So the best one roughly around turn on and turn off time about 2 milliseconds. But recently we also using one of these additives to enhance this switching voltage. You can see that the switching on, the threshold voltage from 35 to 20, from fully on to about 65 to 38. So lower that switching voltage, but you also sacrifice a little bit in terms of your response time to roughly around 10 milliseconds. So on and off roughly around 5 milliseconds. So here is the electro-optics property of that material. It also lowers, not just lowering this threshold voltage, but also lowering this turn-on voltage, and that's the response times of the device. So I guess here in this set of information tells you roughly the response time increase with increase in the cell gap, reducing the line space, electrode width, you're able to improve that threshold voltage, to optimize that. This can be done with a little bit more simulation. Using this software program, you can do some simulation of this electric field strength and then the direct orientation inside of the cell. So typically they run about 6 volts per micron, and then the response time is also fast. It's about half a milliseconds. Okay, so we switch to the gears to different type of device. So before we go into the next topics, any questions about this field-induced divergence? There's one.
This temperature, I can speak louder. This temperature range for the blue phases is very narrow. I think 1 Kelvin. How wide it should be that it would be applicated?
No, the material we have is room temperature and roughly around 7 degrees right now, and we are working on to enlarge that. But in the past, the material is roughly around 1 degree Celsius, so it's very impossible. The other option is using network to stabilize that, and the polymer network formation is in the localized in the defects area, so to minimize that energy, because it's kind of heterogeneous material. So once this the defects get stabilized, and then so you change the temperature, they kind of serve against as a kind of retention, structural pose, something like that, additional pose. So once there's an earthquake, by shaking, and it doesn't.
How wide do you would like it to be?
I think Professor Cole has some material is quite wide, 40 degrees to 60 degrees Celsius. Huh?
Minus 20 to plus 80.
Oh, you see the max 20 to plus 80. So that's the new record. So this is more like high TC. You gradually raise the temperature range. He didn't publish that. Okay, you see that he kept that for secret for himself. So you better ask him those more important questions. But the other one is using the polymer network, roughly around 6% polymer network. It's published by Kikuchi, in 2002, working with the Kyushu University group. And what they did is the polymer network kind of formed in the network in the defects area, and that extended the phase range around room temperature to about 50-60 degrees Celsius. So the temperature-wise is roughly around 40 degrees to 60. It's not really 0 degree. I think sometimes the best sample you have, you report that, right? So you can repeat that. It's difficult to reproduce that temperature range. But I think in general, right now they get broadened by different methods. Professor Cole's methods using twin messages, and the other one is using this polymers inclusion. Did I answer your question? Okay, good. Any other question? There's another one.
You said the pitch was 200 nanometers. Is that the pitch of the equivalent cholesteric, or is that a measurement of the lattice of the glucose?
You say the pitch is about 0.2 micron?
Yeah, well that's what it said on.
Oh, okay.
So I'm just wondering.
It doesn't have to be that range. It can be smaller than 0.1, but the shorter the critical pitch, the higher the switching voltage because viscosity.
Is that a measurement of the equivalent cholesteric?
That's a good question. Yes.
Or is it a measure of?
No, it's a measurement of cholesteric. I think.
Okay.
Yeah. It's a very good question. Anyone else? Okay, so without further questions, we will take another. What's the next? What's the end of the lecture? Okay, we have about 10 minutes. We have a delay, so we have 20 minutes. Okay, well, I guess I spent about 10 minutes for talking about this Bragg reflection device. So you can use the electric field, induce the color change in this polymer stable at blue phase. Earlier we saw this Bragg reflection doesn't change as a function of applied fields, and here we show this field induce the colors, change. So how that works? As I explained to you earlier, I stand too close to that. I guess that's the problem. So. As I explained earlier to you that we change the color, of Bragg reflection is depending on the lattice size. The lattice of this cubic phase, it get compressed or get elongated. Okay, so in this case, that the switchable color is you have these applied fields, but here is the different. Here is the top-down electrodes instead of implant fields across. So in that case, that it can be elongated. The lattice can be enlarged. So the Bragg reflection wavelengths can be changed from a blue to green to red. So would that work for general materials across the board? Certainly not. But maybe we can try this Professor Cole's new material to see if that will work. For blue phase materials, you see, without any other heterogeneous species put it in, you can see that once you increase the voltage from 0 volt to about 45 volts, the cell gap is about 10 micron for this case. So the cell gap is 10 micron. You apply the fields and you see that the Bragg reflection wavelengths do shift. And this has been known for years. This is not the first discovery. They are shift normally around 30 nanometers either way. Depends on what kind of cell structure, right? Your implant field, it shifts to the blue, you make the blue shift. If you have a top-down electrodes, these top-down electric fields, then you shift to this longer wavelengths by enlarging the lattice. So in that case, you see the drop in this Bragg reflectivity too. What does that mean? Drop in Bragg reflectivity? Does anybody know? Why this one? Why this one decrease in terms of reflectivity? Okay, we will get into the answer quickly because we have a limited amount of time. So anyway, you can run these fields up and down, with different kind of applied voltage, And here is the samples. You see that 0, 30, and 35 volts, and that you see when this field induced. The color change starts from this defects area. The defects created by this spaces, and when you turn the field off, it goes back to that. It doesn't go back to the original state. It goes back to somewhere in between here and there. Okay, so it will take a while to go back to this dark state. And this is some of the polymers put it into the samples, and then you can see that induce the phase structures, and it shows the microscope texture shows there's a ratios here. You see, once you put in some hysteresis, some of the heterogeneous material, it takes some voltage to unwind the helix lattice, and then it suddenly goes back to the original state. Okay, so here's the colors of cells. You see that nicely. That show the blue, green, and red. And then the outside of here is still remain the blue. So that tells you that this is not just you use the a paintbrush to paint it on your cell. It's the kind of field induced effect. And you see that and then this one can run back and forth between the two different colors. Well, temperature-wise, it's interesting. It's slightly stable across the board as a function of temperatures, and you start to shifting once the temperature increases to some extent. And then this one without the polymers, I think it shows some of the shiftings into the redshift, and then change this break reflection. Well, I think most interesting is the art. Okay, what am I showing you this morning? What have you learned is you see that you can use liquid crystal to direct the formation polymer nanostructure. Okay, and here is also nanostructures of polymer, but I think the size is slightly larger. Here is 20 micron. This is more like a water lily-like. Have you ever seen a water lily? Right? The water lily in the summer, in the pond that they grow, there's a stems at the bottom, and then there's a big leaves on the surface of that. Oh, it looks like this is a top substrate. This is one substrate. That's the other. You kind of yank them apart, and then so you tell from the center. So it looks like kind of a symmetric, structures on both surfaces, and it linked to the center. So wherever there's a defects, they form around the defects, And this is some cells with no alignment, a cell without alignment. Well, with cell with alignment, you change the morphology, right? We learned that earlier because of the free energy of the system changed. You added another term of this surface. So with that, it changed the morphology. It shows this sponges like the sponge doesn't kind of corresponding to the size, but the sponges, the wall surface is also quite small. I think they are sub microns range. The holes of those defects are roughly around 5 micron, range from 1 to 5 micron. So I guess response time measurements, we just quicken that study. It can be, depends on the applied field and voltage. That it can be as short as roughly around half a microseconds. So I guess I stop right here. I think it's enough of this, device. And I don't. There's a Morse code, from the ET, tell us that about time to take a break. Okay, so I guess that's about it. I without going through that conclusion, I stop right here, answer your questions, and we will have a good time for a longer coffee break. Anybody have? Okay, there's a follow-up.
Why increasing the field intensity was reflected intensity? Increasing, I don't know. When you were increasing the field and increasing the electric field, the reflected intensity was lower. And in the other picture, it was
quite uniform. With polymer, it retains the structures, the lattice structure size, and enough, so you get enough of this cubic lattice inside of the cell gap, in between the cell gaps, so the reflectivity is proportional to whatever size is that. In cholesteric, that's a good question too. In cholesteric, normally to have a saturated this break reflection, it requires at least 8 to 10 pitches. Okay, so you get the maximum. I think that there's a publication by one of our ex-director, with his research associate in 1996, 90 somewhere around that, 96 or 97. There's a paper that talking about the simulation, also a corresponding measurement, that the saturation intensity of break reflectivity is roughly around 8 to 10 pitches. But in this case with polymer, that's why the question I asked earlier. But now you ask me a question back. Without the polymer, I think that it's very big to get pulled apart, distorted of those lattice structures. So you don't have enough of those lattice that maintain that break reflectivity. With polymer, then you get to keep those numbers or this population, concentration or whatever you want to define it. So you get more like a uniform across the board when you switch the color. Did I answer your question?
But the second picture, when you increase the electric field, increasing the field, you have.
This is increase the field. That's decrease the field.
Yes.
Yeah. Well, you also drop a little bit towards the end. Yeah, but here it's once you decrease, going back, you increase the number because of the electric size is smaller, so you get the higher concentration. When the volume expansion, the dilation process took place, and it kind of shrink that numbers of cubes that are available for those reflection. Okay, any other question? Oh, well, I guess everybody is kind of quiet, so I guess movie stops right here. Thanks for your attention, okay? Bye.
Okay, we will resume in 15 or 20 minutes from now.
What's your Windows?